Thank you. So today I'm going to be talking about some research my group has been doing on estimating the fitness cost and benefits of antibiotic resistance, especially for bacterial pathogens. And we're doing that increasingly from pathogen genomic data. But first, I'm going to define some of the terms, of course. So the outline for this talk is going to be basically, I'm going to explain what I mean by fitness, benefit, and cost of antimicrobial resistance. Maybe it's obvious to some of you, maybe less to others, but it's always good to sort of review and see what we mean by that. And then we're going to look at some methods that have been around for some time, actually, using compartmental transmission models to estimate fitness costs and benefits. Okay, and so I'll show you some examples of that and exactly what I mean by that. And so this type of method have been around for some time, but what's really new in the research we've been doing recently is to try to incorporate pathogen genomic data into this type of models. So I'll show you exactly how we do that. And one of the sort of key ingredients for how we do that is that we use dated phylogenies. So again, I expect some of you are already familiar with that, but I will review briefly how that works. And once we've got a dated phylogeny, we use phylodynamic methods to link the phylogenies with the dynamics. And that's what allows us to integrate genomic data into the model. So I will be explaining all of those things in detail, of course. And we're going to focus mostly on Neisseria and gonorrhea for this, because that's what I've been using a lot for my research. But it's really just an example. In fact, the methods I'm presenting today are very generally applicable, I think, and you could apply them to a lot of different systems and a lot of different antibiotic resistance. Okay, so starting with the fitness benefit of resistance, I think that's probably the most obvious thing, that there's a benefit from the point of view of the bacteria to being resistant, because of course, when treatment is being applied, then the bacteria will not die if it's resistant. And that's why we see that the more you use a certain antibiotic, the more you see resistance to this antibiotic. So it's a really out-of-date figure here from an old Lancet paper, where we see that country by country, the more each country uses penicillin, in this case, the more we see penicillin-resistant strep pneumo in those countries. So there's a lot of evidence for that, of course, but in a way that's really quite clear what the benefit of resistance is. What's perhaps a bit less clear is the fitness cost of resistance. And it's something that, again, has been understood for some time, that very often, more often than not, in fact, resistance comes at a cost to the bacteria. So, okay, so it's great to be resistant, it's great to survive treatment, but typically there's a cost. And so there's been a lot of studies that have been done on that. And here, this table is a review from 15 years ago now, in Nature Review Microbiology, where they were reviewing lots of different studies. You see all the references in the last columns, lots of different studies for different bacteria and different resistance to different antibiotics. And in each of those studies, they were looking at the cost of resistance, and they found typically that there is a cost. So where it says yes in the cost column or where it says variable, it's really quite rare that it says no. And the way they assess that in the studies is that they would do like perhaps an in vitro assay to see if the resistant bacteria grow as well as a sensitive one, or sometimes they use animal models as well, or sometimes some studies are even in humans, as you can see. But so very often we find that there is a fitness cost to resistance. Okay, and that's really encouraging, because that means if we can keep the benefit lower than the cost, then we shouldn't see too much resistance arise. Okay, and so that idea again has been around for some time. In fact, the full title of this paper by Anderson and Hughes was something like "Can we reverse resistance?" question mark. And so a lot of and that's an idea that has been around for some time. And so one way to try to really appreciate, so the problem is we don't just want to say there is a fitness cost or there is a fitness benefit. Yes, there is, and we can almost assume there is more often than not. The problem is that we need to really quantify them very precisely, because if we don't know exactly what they are, then we cannot make sure that the cost remains higher than the benefit, for example. So we need to quantify them, and not quantify them in like in vitro assays, because that tells us there's a cost, yes, but it doesn't tell us about the cost like in practice, when infection happens. And so there have been a number of studies looking at estimating the cost and the benefit of fitness using typically compartmental models for the resistance dynamics. So you can see this is quite an old paper here by Austin, who I think at the time was in the group of Roy Anderson, one of the sort of key founding fathers of infectious disease epidemiology. And so compartmental models, again, many of you might be familiar with. Maybe you're familiar with the SIR model, you know, of how those models consider people becoming susceptible and infected and recovered, SIR. Of course, they can be expanded to have more than just 3 compartments. In the case of SIR model here, we have this model that was proposed by Austin et al. So again, 25 years ago, where they consider, you know, individuals start uncolonized here in the top left corner, and then maybe at some point they become infected, and they can be infected either with a sensitive strain or with a resistant strain. Okay. And when they're infected with sensitive and resistant strain, assuming they're not treated, then they are infected. But when treatment is being applied, which happens when you go to the right side of the diagram, then either if you're infected with a sensitive strain, it's going to become uncolonized because the treatment is successful. But except if a mutation happens just then, becoming resistant, that can happen. That's quite unlikely, I guess, but that can happen. We know it can. But the key difference is that for the resistant strain, of course, treatment is not going to cure it. So instead of becoming uncolonized, we move to this treated resistant compartment. So it's probably the simplest model you can have here with just 5 compartments that models how people become infected with either the resistant or the sensitive strain. And as a result of that, and depending on the fitness cost and benefits of resistance, they're going to, the treatment is going to be successful or not. That's as a function of the benefit of resistance. But perhaps also we can integrate the fitness cost. And of course, that's what they did in this paper by considering perhaps that you're slightly less likely to be infected with a resistant strain. That would be incorporating the cost of resistance into the model. So what they did in this study is that they parameterized their model. So we need to say exactly at what rate those different transitions happen, right? And that's going to depend on some parameter values, which represent the fitness cost and the fitness benefit. But once you've done that, you can make predictions for how resistance will increase as a function of how much we use an antibiotic. Okay, and so here's an example of applying their model to data on beta-lactamase producing M-cataralis in Finland. And so there was this increase by about 60% in the use of cephalosporins in Finland between the 80s and the 90s, as you can see. And at the same time, and that's what the dots and the bars show us, we had an increase in the data. We see there's an increase in the percentage of resistance to cephalosporins in this bacteria. And the line is what the model predicts. So in this case, you can see the line fits really quite well with the data. So in other words, the model is well calibrated to the data. It's telling us that the model is capturing something like what really happens when you increase the usage. You see an increase in resistance, and that is a clear effect of the benefit of resistance, right? But we also have situations like this one, looking at a slightly different data set, penicillin-resistant strep pneumo in Iceland, again from the same paper. And what's interesting in this case is that there was actually a reduction in the use of penicillin between 1992 and 1995, apparently. And there was a reduction in the use of penicillin because there was so much resistance of strep pneumo starting to appear, and other bacteria as well. And what we can see in the data, again, the dots and the bars, is that there was actually a reduction in the resistance when there was a reduction in the usage. And that is because there is this fitness cost. Again, the model captures that very well. The model is shown by what the line shows. The curve shows us what the model predicted, and the model predicted a very, very similar decrease. It's not a complete decrease, unfortunately, but a very similar decrease from maybe like 20% down to 15% in the percentage of resistance, given that we reduce the penicillin usage by about 13%. And what's great about this model is that we can, once you've calibrated a model like that and you find it fits well with your data, you can make predictions. In this case, we can predict what would have happened if penicillin use had not been reduced, which is this no intervention curve at the top, then we would have seen no decrease, of course, in the resistant percentage. It would have remained around 20%. So once we've got a model like this that is well calibrated, we have the parameters that correspond to the fitness cost and benefits, then we can make predictions, and that's very, very valuable because we can then make some recommendations for how the antibiotics should be used in the future. So that's obviously, that's one, I think that's probably the first study I could find that was using this idea. But of course, that's 25 years ago, so you can imagine a lot more has been done since. With a PhD student of mine, Lilith Whittles, we were working on a very similar model almost 10 years ago now. We were trying to estimate the fitness, benefit, and cost of cefixime resistance in Neisseria gonorrhea. And so this is the data here that we had. Cefixime resistance, the percentage of cefixime resistance is shown by the, if you look at the blue bar, especially, that tells us in MSN, men who have sex with men, that the percentage of cefixime resistance rose dramatically between 2005 and 2010. And that's because during that time, the first-line therapy to gonorrhea was cefixime. So we were prescribing a lot of cefixime, and the reason why in 2005 they had switched from ciprofloxacin to cefixime is because gonorrhea had become resistant to ciprofloxacin. So that's, I'll say more about that later. But we have this problem with gonorrhea that every few years we change the antibiotic recommendation. So in 2005 they changed from ciprofloxacin to cefixime. Then in 2010 they had to switch to a dual therapy of cefixime and azithromycin. And we are really running out of options in terms of which antibiotic to recommend, because every time we use an antibiotic, a few years later, we see such a dramatic rise in the resistance because of the fitness benefit of resistance. But what's also interesting is that when we switched away from cefixime, so the red bar here represents how much of the prescription were cefixime. So in 2010, the first-line therapy became ceftriaxone and azithromycin. So obviously the number of prescription of cefixime went down dramatically. We also see at that time a reduction in the number of cefixime-resistant gonorrhea. And that tells us that there is a fitness cost to resistance, because if there was no cost, then there's no reason why we should see this decrease in the resistance once we stop using the antibiotic, right? So we built a model very similar to the one I was showing before in PNAS. It's just slightly more complicated, but you have the same basic idea that we have individuals that are susceptible at the top here, and they can become infected either with a susceptible version of gonorrhea on the left or with a resistant one. And if they are, so the model is slightly more complex because, of course, in gonorrhea, there's a latency period which is captured by this U compartment, and then individuals we know can be either symptomatic or not, which is this E compartment represents the symptomatic individuals, and the asymptomatic individuals. But the basic idea of the model is that, and then treatment is applied, so either treatment with cefixime or treatment with another antibiotic. And you can see the model is perfectly symmetric between the susceptible and the resistant side, except for two places, which are the two red arrows. And these two red arrows represent the fitness cost and the fitness benefit of resistance. So if you're infected with a resistant strain, then you're more likely to recover by yourself, which is this alpha nu instead of nu in the susceptible model. Your alpha times more likely to lose the infection just without treatment, okay? And so that captures the fitness cost of resistance. The resistant strain is less fit. We don't know what alpha is. That's the problem. We try to estimate that, but we'll be able to estimate that from the model. The other difference is here for this red arrow, where we have that if you treat an individual who is infected with a resistant cefixime strain and you treat them with a cefixime antibiotics, then instead of just curing the infection as would happen with the susceptible individuals, there's a probability phi that they are not going to be successfully treated. So phi represents the probability of unsuccessful treatment. Again, we don't really know what that is, but it's something that we can estimate from the model. So we fit this model to the data that I was showing you on the previous slide, and we can estimate the different parameters of the different transitions that happen in the model, right? And so the two that are especially interesting for us are these alpha and phi values that we have at the bottom that represent alpha, the cost of resistance, and we found that the resistance strain is something like almost 2 times more likely to go away than the resistant one. So that represents a clear cost. And the clear benefit of resistance is this phi, the percentage of treatment failure that is going to happen when you treat cefixime-resistant infections with cefixime. We estimated that to be something like 80%. It could even be as high as almost 100%. So meaning that the cefixime resistant strain is not going to be cured if you prescribe cefixime almost all the time. So having estimated those different parameters from the data, now we can make predictions about what would happen in the future if we started to use cefixime again. Because cefixime, as I was showing you in the data, so cefixime resistance went down dramatically after we stopped using cefixime. But now, since we are so short of options for treating gonorrhea, we had decided that maybe we could start using cefixime again since the resistance is so low. But what we don't want to do is go back to 2005 and recreate a situation where cefixime resistance is going to arise again. So we estimated based on our parameter values how much cefixime we could give to individuals, or what percentage of individuals we could prescribe cefixime to, rather, in a way that the number of in a way that resistance is not going to arise again. And so if we look at here for each of these diagrams, on the x-axis we have the percentage of prescription or the proportion of cefixime of individuals with gonorrhea who we will be giving cefixime to. As long as we keep that around 20 to 30%, we estimate that the number of cefixime resistant strain you see will not rise dramatically, and the proportion and the overall incidence of gonorrhea is not going to increase dramatically either, and you won't see a decrease in the susceptible because the resistance one doesn't become very successful. So it's a slightly out of date study, this one, of course, again, and we're not using genomic data here at all. We're just using the data from the figure I showed you, but you can see very clearly how once we estimate those parameters, we can make some predictions and therefore some recommendations for how to use antibiotics. Now, the next piece of the puzzle is how do we use genomic data in this context? And the way we're going to be using it is to first use the genomic data to build a dated phylogeny. So I'm sure you're very familiar with phylogenies, right? How trees can show the relationship between different genomes. Standard phylogenetic method reconstruct a tree in which the branch lengths are measured in unit of evolution, maybe the number of substitutions per site or something like that, if you use like PhyML or RaxML or any of those tools. And that's great because it shows us how the different things are different or similar. But what's even better is to reconstruct a dated phylogeny. And what I mean by that, again, you might be familiar with that, especially if you've been using BEAST, you will be familiar with that. A tree in which the branch lengths are going to be measured in unit of time, so maybe in years, in which each genome is aligned with its known date of isolation, and the ancestors of the tree are aligned with the estimated date of when these ancestors existed. Okay, so here in the example, we have 2 genomes that were sampled from 1990, 3 genomes from 2000, and 3 genomes from 2010. And so in the phylogeny, you can see the scale is in years, and each genome is aligned with its known year of isolation. And what was not known in advance is, how old, for example, is the root of the whole tree, but that has been estimated to be around like 1972 in this case, the most recent common ancestor of the whole sample, the root. That has been estimated, and the way it's estimated is that we need to estimate at the same time how quickly the rate of the molecular clock. That's the number of how quickly mutations accumulate in the genome. So BEAST, for example, estimates jointly the clock rate and the date so that you get a tree like that in which the ancestors are aligned with their date. And that's very, very useful in any case to have a tree like that instead of a sort of standard tree, because you can say straight away, well, maybe in 1972, you know, something happened or didn't happen. And that can confirm just by itself some hypothesis maybe you had about how the bacteria evolved. So Beast is probably the most famous software for doing this type of dated tree reconstruction. I would like to mention also my own software to do this, which is called backdating. And that's based on a slightly different idea. The idea of backdating is that it takes as input a standard phylogeny, one where the branch lengths are in units of substitution, you know, the kind of tree you would get out of 5ml or RAXML. And it takes this as an input and the dates of the isolates, and it will build a dated tree based on that. So it's much more scalable to do it this way than with Beast, because you break down the problem into 2 steps. So here's an example where backdating was applied to a simulated data set. The simulated tree was the one shown in A. But what we gave to backdating is a tree in B, where we have no notion of where the root is, and the branch lengths are measured in units of substitutions per site, or number of mutations, probably in this case. And so what backdating did is to estimate the rate at which the bacteria evolve, which is shown in C, and you can see here it works perfectly because it's a simulated data set, and it has correctly reconstructed the correct dated tree in D, which looks just like the one we had in A. So that can be very helpful if you want to build a dated tree. Firstly, it's more scalable than Beast, and it also has the advantage to that it can take as input, for example, a tree built using clonal frame or gubbins, which have corrected for recombination, and that can be very important. So just to give you one example of that, here we were dating the famous data set PMEN1 from Cratcher et al. 2011. We were dating it first using a tree that was not corrected for recombination, and you can see that the plot looks like a mess, really. There's no a temporal signal here, and the date of the ancestor is really unprecisely estimated and really doesn't make any sense. Contrast that with what happens when we pass on a tree built with clonal frame ML, then the temporal signal looks really, really much better, with a very clear correlation between the dates of the samples and their root to tip distances. And we have a very tight estimate for when PMEN1 emerged around 1970, which we know correlates with what we know about PMEN1 and the fact that it became successful due to antibiotic use. So as an aside, really, it's important to build dated phylogenies to account for recombination in the way you build dated phylogenies, and one way to do that is to use something like clonal frame ML followed by backdating, so that you get a tree like this one. So how is this dated tree going to help us understand the fitness, cost, and benefits of resistance? Well, the last piece of the puzzle that we need is called phylodynamics. And again, that's an idea that has been around for a long time, and many of you might be familiar with this, but I will still sort of briefly outline how that works. So phylodynamics is the idea that past population size dynamics affect the shape of the phylogeny that we see. So for example, if the population size increased like this, then the phylogeny we see might look like the one on the left-hand side, right? And in the context of all the bacteria that existed over time. And so the phylogeny we see looks like the one on the bottom left. Whereas if the population size was decreasing over time, then you're going to see something very different. You're going to see that the recently sampled individuals find common ancestors quickly, whereas they take longer to find common ancestors further in the past, because the basic idea is that the larger the population, the more it takes time to find common ancestors between pairs of sites. So pairs of bacteria. So if population size affects the phylogenies that we see, then the idea of phylodynamics is to do the reverse, is to say, well, what does my phylogeny tell me about my population size? Was it increasing or decreasing? So we can use this idea to predict past population size dynamics from a tree. Again, that's an idea that's been around for a long time. Ollie Pybus in Oxford is probably one of the sort of first person to really introduce this idea and show how well it can work. Just one example of using that idea here to the USA 300 clone of MRSA. We were interested to reconstruct. So we built a data tree. I'm not even showing you the tree here, but we also built. We use phylogenetic to estimate, or on the bottom left here, the past population size of this lineage USA 300, which is something like what you might call a skyline plot, right? But perhaps even more important than that, the skyline plot is to look at the growth rate of the bacteria, which is simply how the effective population size changes over time, right? So you can see when the growth rate is greater than 0, then you have population growth, but when the growth rate goes below 0, around 2005 here, then the population size starts to decline, right? And you find that this growth rate that was estimated using the genomic data maps almost perfectly in this case with what we know was the beta-lactam consumption over the years, with an increase from 1980 to 1990, and then a decline following that because MRSA was becoming such a big problem. And we saw, as a result of this decrease in the use of beta-lactams, we see a decline in the growth rate. And when the growth rate goes below 0, then you see a decline in the population size. So you can see here how we're using phylogenomic already. As that was, again, a good few years ago with my colleague Eric Volz at the time at Imperial College. We were looking at using phylogenomic to understand the population size and to demonstrate really this link between the consumption of the antibiotic and the spread of the bacterial pathogen. But so we can do that also. We can also incorporate this idea within models, compartmental models, such as the ones I was showing you before. And so that brings us to this study by David Helekal, who was a PhD student of mine at the time, where we were bringing all those ideas together to estimate the fitness, cost, and benefit of fluoroquinolone resistance in gonorrhea using genomic data. So that's the key difference with what compared to the previous study I was showing you, is that now we're using genomic data. So the data we had looked like this. So we built a data tree, which is shown here, and we know for each isolate whether it's resistant or not to different antibiotics here. And we also know the level of prescription of fluoroquinolone is the one that we, or different antibiotics, but fluoroquinolone is the one that we're really interested in for this study, because we can see that fluoroquinolone was being prescribed a lot between, so in yellow, which was prescribed a lot from the start of the 90s up until 2005 and 2006. And then there was a sharp decline in the use because, of course, there was so much resistance to fluoroquinolones at the time. But we have three lineages in this tree. One which is susceptible to fluoroquinolone. If you look at the first column, like ciprofloxacin, the first one was resistant to this first lineage here is susceptible to fluoroquinolone, whereas we have two lineages, resistant 1 and resistant 2, both of which are resistant to fluoroquinolone. And so it's going to be very interesting to see how the phylogenomic of the different lineages change, and can we link that with the usage of fluoroquinolones over the years. And so these are the results. So very similar to previously, we estimate based on the data tree the prevalence of the two resistant lineages over the years. So resistant lineage 1 on the left and resistant lineage 2 on the right. And again, so you can see it went up quite a lot up until about 2007, and it went down after that. And similarly to the previous study, what's even more interesting is to look at how that changes over the time. So this R of T variable, which represents the growth rate in the lineage, if you want, which when it becomes below 0 means we have a decline in the population. Okay, and so you can see already that this RT here, what we estimate about the growth rate of this lineage, looks a lot like the profile of usage that we have for fluoroquinolones. So there seems to be a very strong correlation between how much we use this antibiotic and how well those lineages spread. In fact, so we fit a compartmental model, very similar to the one I was showing before for cefixime. We fit a similar compartment that has within it the cost and benefit of resistance to fluoroquinolones. And so we can estimate exactly those parameters, the benefits of resistance and the cost of resistance were estimated here for the two lineages 1 and 2, and we did that sort of separately for each lineage, but we found actually that they have very similar profiles in that they have very similar values for the fitness benefit here, maybe a slightly higher fitness benefit in resistant lineage 1, but it's not clear, and very similar fitness cost in both were estimated. Okay, so the two lineages have very, very similar profiles. And so having estimated those cost and benefit, we can make suggestions again about how much fluoroquinolones, which hasn't been used against gonorrhea for over 20 years now, could perhaps be reintroduced as a treatment alternative for resistant gonorrhea in a way that we make sure that resistance is not going to emerge again by keeping the cost higher than the benefit. There's quite a strong negative correlation between what we estimate for the fitness cost and the fitness benefit, and that makes sense because there's, in terms of how the data is informative about those two parameters, there's a negative trade-off that you could have a slightly higher benefit and slightly lower cost, or slightly lower cost and higher benefit, and that would create similar dynamics to some extent. So it makes sense that we have this negative correlation between what we estimate for the two parameters. And again, so the difference with the previous study is that here we were doing that purely using just the genomic data. We didn't input the number of cases of gonorrhea that were resistant or sensitive. I don't think that data exists anyway, because we're talking about before 2000. We really just looking at how the genomes are related and what that tells us in terms of the phylogenetic about the population size of those lineages. Okay, so that brings me to the end of my talk. So just to conclude very briefly, so there's a clear fitness benefit of resistance, and we see that, and that's because, of course, antibiotic usage creates this fitness benefit, and we see resistance emerge and spread when we start using an antibiotic too much. But it's worth bearing in mind that resistance typically also has a fitness cost. And so we can build models to estimate those costs and benefits. It's usually done using incidence data that's been done for many years, like going back to the Austin et al. Study I showed you from 1999. But in our most recent paper, we showed how you can also do that using genomic data through the use of phylogenomics, and you could be doing that in addition to incidence data or instead of incidence data when the incidence data is not available. And so the key idea is that once we have estimated the fitness benefits and costs, then we can make recommendations for how antibiotics should be used in a way that we're going to treat some individuals successfully, but we're not going to see resistance emerge and spread as fast as it did before when we were using antibiotics without any notion of the fitness benefits and costs. Okay, I think I'll stop here and I'll